Hello there. I'm Thomas. Welcome to my presentation here for today. I'm going to present about autonomous spaceborne guidance and control. My supervisors, as you probably know them, Manuel and Manuel Soler. So, let's get into it. I'm going to start with why autonomy is necessary for spaceborne mission. Consider a mission going to an asteroid or a moon around in the Jupiter area. In that case, there will be a 32-minute one-way delay or up to 54 minutes one-way delay. That means that anything that is going to have to interact with the Earth will be anywhere from 1 hour to 2 hours late when it comes to the mission. In this sense, it is important for spacecraft to be able to have a decision-making, and having to wait these 60 minutes to 2 hours before taking this decision is way too long to wait. Finally, we have a challenging environment. Consider a very difficult asteroid that's complicated, even a binary system. Then typically in the past we have used human pilots to do these kinds of missions because the system is not developed for it. But of course today sending humans all over the solar system is not something we can do, and hence we need to develop autonomy for these spacecrafts. So what constitutes autonomy? Well, there are three terms that is essential. You have guidance, you have navigation, and you have control. Guidance is the development of science of determining where to go. Navigation is the science of determining where we are currently or estimating our state. And control is determining how to get where we want to go. And my PhD has been focused on guidance and control, whereas navigation is an integral part of my PhD, but I've not developed something explicitly within this domain. So, where are we currently at applied guidance and control? Well, even in the 1960s, there existed algorithms that of course are guidance and control because this is necessary for advanced missions. However, as we progress into the future, we see that there are more and more sophisticated algorithms that do automate and autonomize several parts of the aspects. However, where are we going into the future? Well, it depends, of course, what you mean by autonomy, and it depends on what area you're talking about. With respect to optimality, it is interesting to have an algorithm that is optimal with respect to, well, everything. Of course, we have nonlinear optimization, which is what's typically used. Just throw as much math as we can at the problem, and then do a solver on it. Of course, today, as everybody's probably aware of, there's also AI that might be able to help us with this. We have robustness. Whatever we do have to be robust towards unplanned and unscheduled events. So we have robust control, robust optimization, and again, AI, reinforcement learning, as something that can deal with these kinds of things. And of course, finally, computability. This has to be able to run on whatever hardware we have. And in spacecraft, we have very limited hardware because it has to be resilient towards the environment it is in. And there we have algorithms such as MPC, which is important to me. We have parameterization of algorithms. We have, of course, we can increase the hardware. And again, AI, reinforcement learning, or all of these. But why don't we want to use AI? Well, currently, space is a very high-risk environment and is a high-cost environment. And AI, at least in its current state, typically don't have any guarantees of its performance. You can only show historics and simulations to show, typically it will work, but you can't show mathematically that it does. This is where, while my focus has been comes in. I have developed model predictive control with focus on robustness and computability, and this has the advantages of having theoretical proofs of their performance and convergence. So, model predictive control. What is it? How does it work? Consider a spacecraft. Some of you that have been seen this presentation before might know this, but consider a spacecraft. It acts in an environment, and we have this nonlinear environment here. We have a model, in this case a linear model, to predict into the future. We optimize one of these trajectories with respect to the cost function. So now we have the optimal trajectory where we want to go. And then we execute whatever optimal input that we needed to get where we wanted to go. But as you can see from the animation, since we have a bad prediction model, we didn't exactly go where we want to go. This is where robustness comes in. So MPC, generically, is just repeating this process every discrete time step. So, what can we do with model predictive control? Well, first of all, model predictive control is a very versatile system. It can be purely a guidance algorithm, can be purely a control algorithm, and it can sit either as a top level or bottom level controller, but typically it will be higher up, but not too far up in the control hierarchy. Advantageously, the system I've developed is far up, so it is as an autonomous trajectory generation, but I want to be able to do this on spacecraft graded hardware. So I have developed it to be quadratic and linear. That means that typically we can solve such a problem within 1 to 20 milliseconds on a normal computer, and probably at least within a second on a spacecraft hardware graded system. It's model predictive control, the tube-based method that I have. It has robustness towards modeling uncertainty. It can guarantee constraints. So if we have some safety critical constraint, we have to enforce these. And it has a cost optimal performance with respect to our quadratic cost. And of course, what I've also been focusing on is state estimation robustness. Whatever the navigation system predicts where we are, there's going to be some error in it, and we have to deal with that as well. So how do we do this? Well, we do this with typical robustness compensation, which in this sense is robust invariant sets. This robustness invariant sets constitutes tubes, and more tubes. And you can see an example of that here. So you can see this in this example figure. You see these circles here, that's the so-called tube. And then we ensure that our trajectory follow where we wanted to go, ideally within these tubes. And this is the so-called constrained output tube model predictive control. I'm not going to go too much into depth in this because it's going to take a lot of time, but I can recommend you to read my papers. Okay, so what have I done? What is my research? Well, here's one of the things I've done, circumnavigation scenario around this asteroid Bennu, where we use an image-based navigation system. So that means our position is purely estimated from images, and then we are able to circumnavigate it, as you can see on this picture here. Similarly, circumnavigation and descent on the Eros asteroid is a highly nonlinear asteroid with gravitational effects that works all over the place. You can see in the middle figure here, we start in a circumnavigation phase to get inside this descent cone. Once we're inside the descent cone, we descend. And again, this has to deal with modeling uncertainties and state estimation uncertainties. This will Similarly, I have taken my work, I've done experimental demonstration of this. As you can see here in the middle, we do sort of the similar scenario, but this is now applied on an embedded hardware on the robot that you can see moving here. On the right, you can see computational time, and you can see that it is in the milliseconds compared to a typical NPC. On the left, you can see this NPC that is compared to the one we have developed, and it fails. So we already show we are better than at least the typical very powerful algorithms. Finally, my last research was to take this and apply it to an actual mission that is going to be launched later this year. So ESA's Hera mission is going to Didymos, and as you can see here in the middle, we are trying to do a close approach to this binary system, but we want to be close, but not too close, so we want to ensure that we will never collide. You can see that we successfully do that in the middle here. You can see some other results on the right and left, but of course I recommend you to rather read the paper than looking at this if you want actual more information about this. So, what is the summary of my PhD? Well, over these last years, I've done 5 conference articles, very fun. I have been able to get 2 journal articles, both are going in the Journal of Guidance and Control and Dynamics, and then possibly another one where I'm not the primary author, the third author, and we will see where this goes. I have also done 2 research days. I've been at the Naval Postgraduate School in Monterey, California, where you saw the research that I did there, where we developed this test bench, and I got to take things out of it. I've also been at ESTEC at ESA in the Netherlands, and that's where I work with the Hera team with the Hera spacecraft, where I developed this for the close approach phase. Finally, I've also done various other works. I supervised a bachelor thesis, I was a finalist in the thesis talk, and most recently we had a paper plate competition. I won, obviously not rigged. So that is my PhD in summary. I hope this was an informal, I hope it was a nice presentation for you. But wait, there's one more thing I have to say before saying goodbye. So I would like to thank you all again for listening to me. Thank you for all the good friends and times I had there. I hope I will see you soon again, and enjoy the rest of the PhD presentations. Goodbye.